Howdy and welcome back. We're going to continue today's lesson by getting into singly linked list. First, we'll define what one is, and then we'll get into the default construction as we'll define it, and then move into a pushback operation to add an element to the end of our singly linked list, and finally close out this video with a brief discussion in terms, and you've seen this many times before, as to how we can destruct a singly linked list object. So you heard me say the word object, so we should be thinking type, and in this case, it's going to be a user-defined type. We're going to consider a singly linked list in this class as essentially a specific type of object, which will maintain its own dynamically allocated sequence of nodes. What we're going to see here is that our singly linked list class, as we'll define it here in this course, is going to have two data members. One is going to be head, which will be a pointer to the first node within a sequence of owns that an object of this type will own. And then the second is going to be a pointer to the last element within this sequence. We're going to consider, for the purposes of our discussion, a very trivial public interface. We're going to define within this lesson a default constructor as well as a destructor, and we'll go ahead and implement one of the behaviors together, which will be pushback. Within the activity corresponding with this video, you will go through the same motions that we're doing here. And in addition to that, you will also define push front, or the addition of a node at the place of the head. So before we get into all of this, let's just go ahead and look at how we can translate this UML diagram into an actual class definition in C++. As mentioned, the name of our class is going to be singly linked list. For our discussion, there's going to be a very limited interface, a default constructor, a destructor, as well as a single behavior, pushback. Now, the STL implementation of a list is going to provide a far greater number of behaviors than this, but I'd like to keep our discussion today relatively simple and focused on kind of here's a class that's going to own whose objects are going to own a sequence of nodes. And within this class, we're also going to have, in addition to that sequence, we'll define some behaviors to operate thereon. If we notice here, under the private access specifier for our class definition of singly linked list, we see our two data members. Head, which is going to be a pointer to a node and will serve as the entryway or gateway into our sequence of nodes allocated on the free store. And tail will be simply a pointer to a node as well, which will provide super fast access to the last element within that sequence. So let's begin by defining what it's going to mean to default construct a singly linked list object. For the purposes of our discussion here, that's going to be simply the construction of an empty list. How we will go about that is assigning the values null pointer to both the head and tail data members of this type. And then within the body of this constructor, there's not much else to do. So let's go ahead and construct an empty list using our default constructor and look at how the values of the data members are going to be initialized. So if we write singly linked list SLL, that is going to provide or invoke the default construction of a new singly linked list object SLL. This is going to reside on the stack because it is a named object. Let me draw this out for you quick. Okay, so here's what that looks like up here in green. We have the identifier SLL. It is a named object, meaning its fields are going to be placed onto the stack. Notice here that these values, the data members, have been initialized with null pointers, so they do not point to anything. As we begin building up with the sequence of nodes that SLL will own, we'll see that these will begin to point to objects residing on the free store. But to just, I guess, go through this one more time, head is going to be initialized with the null pointer. So at this point, after the construction of SLL, head's value is null pointer. Likewise, tail value is null pointer. And showing in this silly little diagram over here, we have an empty list. Now let's go ahead and begin pushing things back to our list. So growing it and adding various values to build up a collection of some sort of values of integers. Recall that our node objects are going to store two things. They'll have two fields. One is going to be the data, and in this case, it's going to be simply an integer value. And then there's going to be a node pointer to the next node within our sequence. So let's go back over here. What cases do we need to consider in the pushback behavior? Well, there's going to be two conditions. Remember that, hey, if we're building up a new singly linked list, it's going to start out empty. So in the case of the empty list, we're going to have to essentially create a new node on the free store and ensure that it gets linked up to both head and tail, because at that point we would have a list of one where the head and tail are but the same elements. Now, if we were to push back into an existing list, we're going to have to tack on to the last node within that sequence. So we'll be able to do that through tail, which will serve as our quick access to the last element to add, say, to either receive or get that object, or to go ahead and tack on an additional one into our sequence. So let's look at how we define that behavior. Let's go ahead and consider the empty list condition first. So if we're in our pushbacks, if we have something like a singly linked list, first time through, we're going to be under this condition because we started out with an empty list. So in this case, head's going to be equal to the null pointer. Why? Because that's how we've defined an empty list. If head is pointing to the null pointer, there's no nodes within our sequence. It's empty. So in that case, we're going to assign head and tail the value of the address of a new node all located on the free store that is going to be initialized with whatever value was passed to this function. In the example here, that's the integer value of 7. So how would this look on the free store after pushing back into an empty list? Let's go ahead and draw that out quick. Okay, so right after the declaration here of didn't mind to erase SLL, we currently have the structure or the configuration shown in this diagram down here in green. When we execute the pushback into the empty list, we're at the region of code here highlighted in green, and we're going to assign head and tail the address of a new node all located on the free store. So we'll go ahead and allocate that node. It's going to have the integer value of 7. It's not going to point anything because remember how we defined our node's parameterized constructor. We take the single argument, use it to initialize data, and then we go ahead and initialize that node's next pointer with the null pointer. So it points to nothing. Now, if we look at this assignment statement here, that address gets put into tail, and in turn, the address that was just put into tail is put into head. So we make this link first, and then we go ahead and make that link. And at this point, both head and tail are going to be pointing to the same node in our linked list because we have a linked list of exactly one node. So the head is the tail. Now let me copy this real quick and then we can go through the second pushback here. So give me one moment. Okay, so let's go ahead. So this is the same configuration from the previous slide, and now we're going to want to push back an additional element to this. Let's say it's 11. Okay, at this point, we'll enter into our pushback function where we'll check the condition is whether or not the head is pointing to or is storing the null pointer. In this case, it is not. We have the condition that our sequence of nodes has exactly one element. So head and tail are both pointing to that node storing the integer value of 7. So we're into our else condition. First thing we're going to do is go ahead and store the address of some new node allocated on the free store with that argument. So 11, and how this is set up, it's pointing to nothing, and we're storing it in this pointer called temp. Because remember, new returns an address, and we have to store that address somewhere. The next thing we're going to want to do is hook up tails next to point to this node. So we'll go ahead and say tails next. So that's the node storing 7 is now going to point to the node storing 11. So we've now done that, and we've done that step. The final step here is going to move tail to point to the new tail of the list. So in this case, tail will now point to that node. And then at this point, the function would return the activation record for it would be removed. So temp would be popped off the stack, and we'd have this configuration here. Head would be pointing to the first node in the sequence, which is that node storing the integer value of 7. It's going to be connected up to the last node in our sequence of 2 nodes, that's storing 11, and tail will also point to that last node storing 11. Okay. So here's that same, what we just went through together in action. So let's say we go ahead and start out with a singly linked list, SLL. At this point, we're going to have an empty list as shown that both head and tail are going to be initialized with the null pointer. So as we move through this, if we were to push back the integer value of 11, we would have a sequence of nodes of exactly 1 node. So in this case, both the head and tail will be pointing to the same element. So in this diagram, we can see the head end of the linked list, the tail end of the linked list, the 1 node storing the integer value of 11, and that's its address. And we can see here its address is stored both in the head and tail, and that will provide us access to this element. Now let's say we go ahead and push back the integer value of 7. Looks like I had this in the opposite order in the previous memory diagrams. But anyhow, we're now dealing with a list that has 1 element. So in this case, we'll simply access the tail and add a node storing the integer value of 7 to the linked list. And we can see here that's happened. Look at this point, that head is going to be pointing to the address of the first node. And again, I'm not showing the next pointer within this diagram. I'm just showing kind of a list of integer values. And at this point, tail is going to be pointing to the newly added tail. Okay, and head's next pointer, as kind of, I guess, implicitly implied here, is going to be pointed to the second element in that sequence. So let's go ahead and continue this. Say we push back the integer value of 8. Notice here we're operating at the tail end of the linked list, and because we are, the head's value is not going to change. It's still pointing to this node whose next pointer is connected to that node storing 7 as we set up on the previous slide. However, we've added a new tail. The operation of pushing back 8 has added on to the node storing the integer value of 7. So at this point, we can see that that node is pointing to that new node whose value is 8. Notice that in this case, because we have the addition of a node to the tail end, tail has been updated to reflect the address of the node storing 8. So we've more or less gone through the pushback operation. Now I'd like to go ahead and just cover the destruction quickly before we move on to the next section of this lesson. So over the lifetime of a singly linked list object, what we're going to see here is it's going to essentially acquire, at least as we've structured here, a sequence of nodes that it will own, that each node within that sequence will reside on the free store. At the point of destruction, we're going to have to go through and deallocate the memory associated with each of those nodes. Now the process here has been shown, I guess, a couple of times, once in the previous lesson and another time within this lesson. So I'm going to kind of quickly go over it now, but this will be the first time where we're seeing the code actually placed inside a destructor. So all we have to do here is essentially, while there is a head element, we're going to go ahead and create a temporary node pointer to the next element within our sequence. We will deallocate memory associated with the header that pointed to by head, and then we're going to move head to the adjacent node. So if we look through that process, we start out with our linked list. And again, we can't call delete on head because we'd lose everything after it. So if we were to do something like delete head, the problem with this is we've now lost all of that. So we need a better way to go about this. And in order to preserve that portion of the linked list, we'll go ahead and initialize a next pointer to the two heads next. So in this point, we've now have all of this preserved. We can call delete on head, which will effectively have wiped out that node. Its memory would have been deallocated for. And at this point, we still have access to the remaining nodes in the sequence. We will move head forward one. So at this point, head and next will be pointing to the same element. And then on the next execution of the body of our while loop, head will get moved forward to the next element. We'll then deallocate memory for head. We still through next have the remainder of our linked list, and eventually head will be moved over to that element. In this process, we'll continue for each element within our linked list. So to go ahead and see this kind of in action, instead of drawing out some memory diagrams, let's go ahead and look at the implicit invocation of, say, SLL's destructor. And let's assume at this point, SLL has owns a sequence of nodes with 11, 7, and 8. And let's go ahead and look at what happens. So we can see here as we're getting into our destruction process, head is going to point to the first node within our list. Next, which we just talked about, is going to point to the second. We, of course, would deallocate the memory associated with the node at the head, and then we'd move head forward, and we're now at the case where we have a linked list of 2 elements. Notice here, head now is the node storing the value of 7, and next is pointing to the next node in the sequence that's storing 8. Okay, cool. We'll go ahead and call delete on head, effectively wiping out the node that is storing the integer value of 7, and we'll go ahead and move head forward to that of next. At this point, head's next is the null pointer, and we can see that reflected in the next pointer. Therefore, we're going to go ahead and call delete on head. At this point, this object would be wiped out. We would assign per our destructor, head's going to equal to next. Guess what next is in this final case? Next is the null pointer. And guess what? That was our terminating condition on this loop. So when head's null pointer, we're not executing the body again. And at that point, we are done with the destruction process for SLL or any singly linked list object. One question I guess I have before we move on is, why isn't tail considered a dangling pointer at the end of the destruction process? The simple solution here is we've just destructed the singly linked list, so the memory allocated for tail and head is going to be deallocated anyways after the destructor is invoked. So let's go ahead and move on to traversing a linked list.